Hey everyone, welcome to This Explainer. Today we're diving into a massive, kinda hidden crisis happening right now inside AI data centers, and we'll discover how solving this exact infrastructure problem could actually transform human healthcare. We're going on a really fascinating journey today, taking us all the way from silicon chips to the human soul.
All right, let's take a quick look at our roadmap for today. We're going to start with the AI compute waste crisis, look at the community backlash against data centers, talk about making flops flow like megawatts, the logistics of scaling compute to gigawatts, and finally, we'll tie it all together with AI for end-of-life care.
So, let's jump right into Section 1, the AI compute waste crisis.
There is a huge disconnect right now between the billions of dollars pouring into AI and the actual efficiency of the physical clusters being built. Think of it like a radian. If two lines are off by just a tiny degree at the start, that gap becomes massive as you scale. That's exactly what we're seeing in AI infrastructure today. The fast-paced scaling is causing some massive compounding waste. For instance, recent breaking news reported that xAI's infrastructure was running at a staggering sub-10% model flops utilization, or MFU. Think about that. It's like buying a massive, state-of-the-art factory, but leaving 90% of the machines completely turned off. In this AI arms race, people assume that just throwing money at more GPUs automatically makes better models. But frontier AI, it's a highly complex systems problem. When you just rush to plug things in, you end up with theoretically massive computing power that's practically doing almost nothing.
And to really grasp how wild that is, let's look at Google's historical baseline. For them, a 95% node utilization was the standard. In fact, if it dipped below 95%, they literally considered it an outage. There were just no excuses. You have to iteratively bring these systems up. The pressure of the AI scaling era really shouldn't be an excuse to abandon common sense. Because the margin of error is so much lower now, the financial cost of this waste is just astronomical.
Even if we look back at older frontier models like GPT-3 or PaLM, they were already hitting somewhere between 21 and 46% utilization. Today's best-in-class really should be pushing 60 to 70%. So seeing modern, rushed, single-tenant clusters operating at sub-10% just makes them look incredibly inefficient. It really proves that the whole move fast and break things hacker mindset, yeah, it doesn't work when you're building massive physical data centers.
Which brings us to Section 2, community backlash to data centers.
Because you see, the cost of this waste isn't just a red number on a balance sheet. It's spilling over into the real physical world and creating some intense friction. Right now, up to 20% of all new data centers in the US this year are at risk. Why? Because local towns are pushing back. Residents are understandably worried about strained power grids, environmental impacts, and super complex permitting issues. You really can't just drop a massive, power-hungry facility into a neighborhood without the community feeling the strain.
So we need a solution that actually works for everybody. There's this brilliant thought experiment from Scott Nolan to fix this. What if we charged a 50-cent premium per compute hour to the AI developers? We then take that exact cash and give it directly back to the local communities to lower their own power bills. Instantly, you align the incentives. If a new AI data center moving into town literally means cheaper electricity for your house, suddenly the public becomes partners in the project, not opponents.
All right, let's move on to Section 3, making flops flow like megawatts.
To truly fix the technical side of this waste, we have to completely rethink how we distribute compute. Enter the Independent System Operator, or ISO. We're actually borrowing this concept directly from the history of the electric grid. An ISO is basically a neutral coordinator that pools resources across a network to share supply and demand. And it usually doesn't even own the physical machines itself. It just ensures that no single machine sits idle. If we want AI compute, those flops, to flow as smoothly as megawatts of electricity do, we absolutely need an ISO for compute.
Think about it. Instead of every AI lab vertically integrating and hoarding their own private GPUs, which leads to those terrible sub-10% utilization rates, we need horizontal pooling. This shares resources across uncorrelated sources of demand. It's like having a steel factory that needs massive power at night and a shoe mill that spikes during the day. By pooling them on a shared grid, everybody gets their guaranteed baseload, and they can safely share the spike capacity. It is just vastly more efficient.
Now, Section 4, scaling compute to gigawatts.
When you pool compute horizontally like this, you can efficiently reach a scale of infrastructure that is frankly staggering. For example, AMP's vision targets a 1.2 gigawatt baseload of steady compute. But to handle the uncorrelated research spikes for advanced AI models over the next 4 years, we're going to need to efficiently scale up to 6 gigawatts of capacity. To put that into perspective for you, just 1 gigawatt is roughly the total output of a standard nuclear reactor. We are talking about an unbelievable amount of power, and it can only be achieved responsibly if we're operating as a highly efficient shared grid.
Which leads us to our final part, Section 5, AI for end-of-life care. This massive scale really brings us to the ultimate, deeply human question at the core of all this. With all these gigawatts, these massive data centers, the billions of dollars, and the community negotiations, what are we actually doing this for? How does this raw power practically benefit humanity? Well, the answer might lie in one of the absolute hardest challenges we face, healthcare, specifically at the end of life.
In the US, the medical system generally treats mortality as a terminal point that has to be delayed at literally any cost, and this creates a culture of incredibly vague prognoses. Doctors are naturally terrified of malpractice lawsuits if they get a timeline wrong, so they offer huge error bars, telling patients they might have anywhere from 6 months to 6 years to live. That uncertainty drives aggressive, often very painful treatments. Contrast this with Eastern cyclical views, like in Hindu culture, where death is seen as a step in a journey, and sometimes even celebrated as a liberation. Our Western fear of finality, combined with the fear of malpractice, creates a cycle of immense suffering.
Because of this deep uncertainty and the push to just try everything, over 30% of all Medicare and Medicaid spending in the U.S. is poured directly into end-of-life care. And the heartbreaking result is that patients end up enduring weeks of intense therapies, often suffering in hospital beds during their final days, instead of just resting comfortably at home with the people they love.
But here is where those gigawatts of compute can change everything. By taking that immense power and training AI on massive longitudinal patient data, like Stanford's 12 million patient record database, we can generate hyper-precise end-of-life predictions. We can basically ship the heavy burden of diagnostic uncertainty completely off the doctor's shoulders and onto the AI system. By giving patients actual scientific certainty about their timelines, instead of just a vague guess, we empower them to reclaim their agency. They can choose quality of life and spend their final days doing what they love, rather than being trapped in a loop of desperate medical interventions.
Ultimately, these two massive challenges are deeply connected. If we can figure out how to build net-positive, community-backed data centers that run efficiently, we unlock the raw compute we need to fundamentally solve profound human challenges like end-of-life care. We can empower patients with pure science. So as we watch the billions pouring into AI right now, we really have to ask ourselves, what kind of future will you help build on the grid?